Discover the powerful tool behind quantum wave propagation, how Green's functions predict the future of particles. And here is a great example of what is going to be introduced as a Green's function. Here, this is found from a paper that did a neural response on Green's functions, and this diagram is definitely a highlighting point of it. And what we want here is that the Green's function is a way to solve inhomogeneous linear differential equations, and what that means is that we have, different setups here where we have a del squared operator and we're trying to find out what something may be. And the goal is that we want that something to be a delta function, okay? And the reason will become apparent as we get more into the theory, or if you've had electromagnetism before, you've seen this. But nonetheless, what we want here is we want the delta response, okay? And if you notice, when we take the Fourier transform, which is often used to solve these Green's function problems, we get a point response here, okay? And the point response is exactly the delta response. So if we think about Green's functions as the response to a system of a point source, once you know how the system responds to a point of disturbance, you can use it to determine how it responds to more complex inputs by integrating over all possible disturbances. So keep in mind that we're going to try to get something that ends up in a power spectrum or Fourier transform or resulting in a Dirac delta, which is just a point. And the goal is to find out what is the function that makes that happen. And in this setup, that function is known as a Green's function, and it takes on the characteristics of the differential equation in the system, whereas you need the different boundary conditions like the Dirichlet and the Neumann for the wave function and its derivative to be able to actually find it. So with this, very powerful theorem, very powerful stuff, but let's see what this problem has for us. So in problem 10.8, we want to check that equation 10.65 satisfies equation 10.52 by direct substitution. And here they give us a hint where the del squared or Laplacian of 1 over r gives us the negative 4 pi delta cubed r. So this is just a spherical system here where r is the vector from the origin. And here we reformatted the Schrödinger equation into this form here. Okay, K has the nice 2me over h bar, or square root of 2me over h bar. So here, we have a lot dealing with this equation. And in the book, they call this a quasi or, modified Helmholtz equation, which again, if you've studied, electrodynamics, then you've seen these kind of things before. And what we found through the Green's function and setting it up and solving for it via Fourier transforms and contour integration is that we end up with a Green's function that takes this form. Okay, so the goal is to verify that this function leads to a delta once we plug it in here. Okay, so why do we care? Well, the Green's functions describe how quantum particles propagate, which is exactly what we want when we're dealing in scattering problems. And again, we've seen these in other places, but where? And that's the challenge I have for you. Where else have you seen Green's functions? If you studied PDEs, ODEs, then you've seen them before, but what exactly is the context, or where can we apply them outside of scattering problems? That being said, although everything in the PDF is in the video, if you want the PDF for your collection, please just let me know and I'll send you the link to the Patreon page and you can download it there and you'll be good to go. And if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's jump right into this problem. All right, stop number one. We really just need to verify that the solution actually results in the given equation, i.e. leads to the Dirac delta. So in this case, we really need to calculate the Laplacian, which can be done in a couple of different ways. But first, let's note that the Laplacian of g of r is equal to the del dot product with the gradient of r. Okay, that's how we get the del squared. And that g of r is only a function of r in this case because we saw it was e to the ikr over 4 pi r. And that will be key to us later in the simplification route, which we'll see in just a second. But from all this, we observe that before I can find the Laplacian, I first need to find the gradient. So that's what we're going to do first. So plug it in. We see that we have all of this nice stuff. Take all the constants outside. Rewrite this in an algebraically friendly manner for derivatives. And what we see is that we end up with the product rule here on the first go. Okay, so we have del, or the gradient operating on r, leave the second term alone, first term alone, take the derivative of the second term, and let's go ahead and simplify this into a nice expression. So we have e with the gradient on the inside, r with the gradient on the e, and we're good to go. So when I take the dot product again with the del operator, I see that again constants come out front, and I purposely color-coded it because we once again have another set of product rules. One for the blue, one for the purple. And when we apply the product rule, we see that we get a del, which is now a gradient on the e to the ikr, dot product with this vector, because again the gradient turns a scalar into a vector. Okay, so derivative of the first, leave the second alone, leave the first alone, take the derivative of the second, and then rinse and repeat for the purple. Okay, so we notice that this entity and this entity look very similar and dot products are commutative, so let's go ahead and rearrange this to a more formal manner. All right, so we rearranged it due to the commutativity of dot products, and we see that red and red are the same, so we put a 2 there for it, no big deal. Del dot del gives us the Laplacian, so we have a Laplacian here and here, so we'll put those to the other side. Now, again, what we're going to do is put this in the derivative centric manner. So that's the negative 1 power instead of 1 over r. We're going to leave this one alone because this was the given hint, okay? And now what we see is that we have really just 4 things to look at now. But we're only a function of r, so we only need the first term in the derivative expressions. And let's look at to y. We see that the spherical gradient, which is given as this, again, go see the PDF if you want the other notations for it. So we applied the product rules, so now we need to get on to what are the derivatives we actually have to apply. But nonetheless, we see here that we are good to go up to the fact that we see that we have partials with theta, partials with phi, but the function is only a function of r, okay, in this particular case. So the derivatives of phi and theta go to 0. So we're really only left with the radial component, which is just the derivative, partial derivative of r, which at this point you could write as a total derivative since there is no other variable in this expression, and we're good to go. As for the Laplacian, we see once again this whole hefty beast here. Again, the thetas and the phis lead to 0 derivatives, so if I multiply this thing by 0, I get 0. Multiply this thing by 0, I get 0. So I'm left with this product of derivatives here, and I'm good to go. Alright, so as stated and as with the color coordination, there's really only 4 terms to consider. So I need the derivative of r inverse, the derivative of e to the ikr, again with the r hat direction because the gradient turns a scalar to a vector. And then here I have the hint for that, so I don't need it. And here I turn the spherical Laplacian for the radial component only. So we have lots of derivatives to calculate. Let's get to it. So here, power rule, bring the negative 1 down, take 1 from the power. Chain rule on the e to the ikr, ik being the extra factors. And then here I plug in my hint, again color coordinated, and then we see that we have negative 4 pi delta cubed r. That will be what we want to focus on. Here, after the first derivative for e to the ikr, we just get another factor of ik. We have an r squared here, so that leads us to an r to the third power. Good to go. But note that we can take the constant out front, we can rearrange, put the delta term at the back, and then we could take these constants out front and just focus on the dot product. So the simplification is not that bad. And what we see here is that the dot product of r hat gives us 1. Beautiful. This can be left alone. And we see that after taking out the ik in this blue term, and we realize here that we have yet again another product rule. Derivative of the first, leave the second alone. plus the derivative of the second, leave the first alone. And then from here, we're just going to distribute this 𝐸𝐸𝐴 cubed and everything. And we see that one factor from the cube canceled with one factor from r here. Two factors here cancel with the two factors there. So now we can simplify and run away with this question. So that being said, if you like this content or are finding it helpful, please go ahead and give a thumbs up on the video so that more curious minds like you can find it. And here we can continue to simplify. So we have every term had an e in it, so we just factor that exponential out. After distributing, we see, and simplifying, we see that we have a negative 2𝐸𝐸𝑟² canceling with a positive version. Beautiful. Now we see that once we distribute the 𝐸𝐸𝐾 to the other 𝐸𝐸𝐾 that was found from the exponential, we get an I², which leads to a -1. Cool. We like that. And so here, now that we have two things in the brackets, we're going to go ahead and distribute this into both of them. And what we see upon distributing is that -1/4 pi cancels with the -4 pi here on the Dirac term, or the delta term. And then we have here that we just want to keep that out front and realize here that we could reformat this into the form of the Green's function. Clearly, I had to color code this with green. It's only fitting. But we realize that we have a 4 pi r and an e to the 𝐸𝐸𝐴, so we want to put that inside here and get the k out front. So that's what this step is, k², and then everything here is the Green's function. So the other thing to note here is that the Dirac delta tells us that whatever is multiplied by it has to be evaluated at 1, otherwise it goes to 0. That's in the definition of the Dirac term itself. So this is why we have e to the 𝐸𝐾 times 0. But we know that the exponential of 0 goes to 1. So once we do that, we simplify down, and we see that the Laplacian of this Green function leaves us with a delta term minus a k² g of r term, and that completes our derivatives, leading us straight to our final stop, where we have to evaluate, is this going to hold for equation 10.52? So we see we have the Laplacian operator, k², and the Green's function. And of course, it has to be equal to the Dirac delta response. So, distribute the Green in. We see we get the gradient of Green, which we spent all the time calculating. K² g equals the delta. So we have this result right here. Let's plug it in. And we see that the k² g plus k² g, they cancel. Beautiful. And thus, we actually showed that this Green's function satisfies the equation that we had, and that is beautiful. Again, there's a lot of power in this thing, but this example is just making sure that it works. The example and the proof in the book, or the walkthrough in the book, still has a lot left in it. But if you take the time to learn Green's functions, they will help save you a lot of time and agony in later courses. So definitely get used to them. They're not going away, and they're very powerful. Okay, so a quick video today. Thank you for watching, and I'm glad that we actually started talking about this because they were going to come up at some point anyways. And if you would, please share this with a friend who's also curious about science, and let's grow this learning community together. I have to, of course, give a thank you again to all the supporters of this channel. You make this possible. And if you'd like, please consider supporting this channel by subscribing and sharing this curiosity, or joining the Patreon page or the Buy Me a Book Club via Buy Me Coffee, no account required. This stuff is fascinating, and we need more content that can help give more perspective on these problems, because everyone has access to things online, like all these other resources, but it's important that we have a conversation regarding their ramifications and not just getting to an answer. So that's what I like about exploring these topics in this book. And of course, Griffiths/Schroeder give plenty of ample resource to it. So I think this is a very good idea to keep, going through it. We only have a couple chapters left, so I'm gearing up for what's to come next, but please be aware, if you want to get the future proofing or find out the problem catalog, please go to Patreon, and you can see the link there to join. Books, notes, and other reference materials are found below or in the PDF docs. Please utilize them, because some of the resources I found in redoing these problems are very nice, or mathematical tables, things like that things that you would want if you're studying this long term. As always, thank you for watching, and until next time, stay curious.